There are three main topics, 1, 2, 3, and these are what happens to thermal radiation when it's incident on a surface, and the second one, what a surface emits, and the third one, how two surfaces exchange radiation. So first of all, we're going to talk about what happens to thermal radiation when incident on a surface. Let us first contrast between this mechanism of conduction heat transfer and the mechanism of radiation heat transfer. So as you can see, in a solid, conduction happens through lattice vibration, and the heat movement is through direct contact. Likewise, in a gas, the conduction is also through direct contact between these red molecules that are hotter and the blue that are colder. So conduction requires a physical medium. So it requires a physical medium. In contrast, radiation doesn't require any medium. So we get sunlight, and we know a lot of the space between us and the sun is empty. There is no medium there. So radiation is fundamentally different from conduction in terms of the mechanism of energy transfer, and these are really the two fundamental mechanisms of heat transfer. Convection refers to addition of bulk flow to these modes. You probably already know of electromagnetic spectrum here. The, that refers to a range of wavelength from very short to very long. Okay, this includes, for example, radio waves here, and X-rays are some of the examples. Our interest is in the range from ultraviolet, somewhere in ultraviolet, to much of the infrared. This range is referred to as thermal radiation. This is our interest. So thermal radiation is around 0.1 to 100 micron. These are written in nanometers here. All the electromagnetic waves travel with the speed of light. Their wavelength and frequencies are related by this equation. Again, to emphasize that thermal radiation includes the visible spectrum. When waves are incident on a surface here, a part of it is reflected and part of it is absorbed. Depending on the thickness of the material, whatever is not absorbed is transmitted. For a given surface and for the type of radiation, that's the wavelength of radiation, the fraction of energy that is reflected is termed reflectivity. So reflectivity is the amount reflected over the amount incident. Likewise, absorptivity is the amount absorbed over the amount incident, and transmissivity is the amount transmitted over the amount incident. since these are fractions of incident energy and the total energy is conserved, their sum is equal to 1. This is a very important relation that we will use. If there is no transmission, if this is not there, then we have rho for no transmission. No transmission, rho plus alpha is equal to 1. We will use this information to calculate one property data when the other property is given. For example, so rho is 1 minus alpha. I'm going to now share examples from the biological and environmental applications. So the first one, we see an example of all three properties: reflected, absorbed, transmitted fractions, or reflectivity, absorptivity, and transmissivity, varying with wavelength for a leaf. This is corn leaf. And notice that in the range where you have the maximum absorptivity for chlorophyll, so somewhere in 0.45 or so, and then 0.65, so 0.45 here and 0.65 here, we have very high absorptivity. So a consequence of this is that leaves cannot get shaded, as the lower leaves will not obtain any light. Here is another example of properties varying with wavelength. And this is in the environmental context. So you see reflectance for vegetation, water, soil, and snow. Notice how snow is different from water, and also vegetation and soil are quite different from those two. This one shows the net reflectivity over all wavelength and all surfaces over the entire Earth surface. It's kind of a consequence of the previous slide, depending on what is the predominant surface like in a particular region. Here is another example of a property, in this case reflectance in a biological context. This is reflectance of human skin. And notice that, like we know in visible light, a darker skin looks darker because it reflects less in the visible range. But what is interesting is even outside the visible range, in the near infrared and in the infrared range, we see that it reflects less than the light skin. Okay, so these properties are important in a number of applications. So this one is yet another example of all three properties: absorptance, transmittance, and reflectance of human skin It is very old data, but it's one of the best data that at least I could find, shows all three properties varying with wavelength. So suppose you are warming up in the sun. So the solar energy incident on your skin surface, let's say F0, as it moves into the skin, it obviously decays. Now this energy absorption with distance, or such energy absorption with distance, is quite often approximated as an exponential decay. It's a very simple assumption. So this is the exponential decay of the energy. Now, how to characterize this exponential decay? This exponential decay is characterized by a penetration depth, delta. So the equation to this decay is F equal to F0 e raised to minus x over delta, but this delta is the penetration depth. And let's look at the meaning for delta. At x equal to delta, if I plug in x equal to delta, then I get F equal to F0 e to the minus 1, or 0.37 times F0. So at distance delta, so this is my delta. At distance delta, the energy level is 37% of what it was at the surface. So 63% of the energy has so let's make sure this is 0.37 that we're talking about. So 63% of the energy has decayed over this distance. So this is a way to characterize how easy for this material to absorb energy of a particular type. And what do I mean by particular type? This delta is very much a function of the wavelength that we are using. So here we have the absorption spectrum of liquid water, which makes up for much of the biomaterial. It shows that the delta, and in this case the plot is of 1 over delta, it varies so significantly with wavelength. You can see that it's many orders of magnitude variation. So this is used to advantage in medical purpose, for example, and it has many other biological implications.